Okay, so this video is on the multi-stage R cycle, the refrigeration cycle. So a label might use code. Okay. Now we see our knowns. The low, medium, and high pressures are 140, 320, and 800 kilopascals respectively. Mass flow rate 0.05 kilograms per second. The main mass flow rate. Okay. So first I'm going to put down all my states. You can see there are 9 states for this. And for every state, we know what the pressure is. If we look at our TS diagram, we see that the low pressure is at state 1 and state 8. It's 140 kilopascals. For our medium pressure, it's state 7, state 6, state 3, state 9, state 2. So we'll start at state 2. And our high pressure is from state 4 to state 5. (800 kilopascals). Okay. Now, if we know at least one more thermophysical property value, we could find the rest for at least one state. So if we look at a TS diagram, this is an ideal vapor compression cycle. We see at state 1 and state 3, it's a saturated vapor. So that means it has a quality of 1. And at state 3, now we can find all the thermophysical properties for that state. Going to use real fluids and assume we're using R134A. If you're using a different working fluid, you just put that one in. Fine. Real thermoprops. Our input properties are pressure, which we have, and quality. Then we paste. I'm going to copy and paste this into the state 3. Since we're using the same independent variables, same working fluid, and same two independent properties, quality and pressure, but I need to make sure I change the array elements from 1 to 3, or else we will have an incorrect output for everything. Then if we look at the TS diagram again, we know state 5 and state 7 are saturated liquids. So that means the quality at state 5 and state 7 equals 0. I'm just going to copy and paste this function again and make sure the element in the arrays are 5. Now we have to change them to state 7. Okay, so now we don't know the quality for any of the other states, so we can look to a different thermophysical property value that we might know to find the rest of the states. And we can see that there's an expansion valve, and expansion valves have constant specific enthalpy. So we know the enthalpy at state 5 equals the enthalpy at state 6, and we found the enthalpy at state 5 already because we knew the quality and pressure. So for state 6, we'll do enthalpy at state 6 equals enthalpy at state 5, and now we have two independent thermophysical property values, so we can find the rest at state 6. Thermal properties, real fluids, R134A, real thermoprops, and pressure and specific enthalpy. Paste. Now we need to insert which element in the array we're doing. Oh, sorry, this is state 6. And there's an expansion valve from state 7 to 8, so we can find state 8 because we already know enthalpy at state 7. Go to copy and paste this. And then remember, you just really need to make sure you change the numbers in these arrays. So state 8 enthalpy equals state 7 enthalpy. And here we're using this function to find all the thermophysical property values at state 8. And there are no more expansion valves. We can see the only state we need now is state 9. We need state 4 and state 2. State 4 to 9 is through the high pressure compressor. And since it's an ideal cycle, we're assuming the isentropic efficiency of the cycle is 100%. So that means S, the specific entropy at state 9 equals the specific entropy at state 4. And we don't have either of those knowns yet, so we can't determine that. Here we have specific entropy at state 1 equals specific entropy at state 2 because of the low pressure condenser. So we do have the specific entropy at state 1, so we can find 2. So we know S2 equals S1. Options, function info, thermophysical properties, real fluids, R134A, real thermal props. Then we have pressure and specific entropy paste. This is state 2. Now all we need left is state 4 and state 9. Look at state 4 and state 9. We can't use temperature. We already used pressure. Regarding state 9, state 9 doesn't have the same temperature as any of these other states. We already recognized the pressure. For specific volume, I'm not sure. Enthalpy. Entropy. Okay, so we know that the entropy at state 4 equals entropy at state 9. We don't know entropy at state 9 yet, but we're just going to fill it in like we already know. So we have pressure, entropy. This is and this is because isentropic compressor. And then again, state 1 to 2 was a isentropic compressor. Okay, so now back to state 9, which will be a final state, and then we will be done. We see that this is a mixing chamber, and we can assume that this mixing chamber is adiabatic. So that means that the heat into the mixing chamber equals the heat out of the mixing chamber. With also our first law of thermodynamics. So if we do a mixing chamber energy balance based on the first law of thermodynamics, we know that m dot 2 times H2 plus m dot 3 times H3 equals, so this is energy in equals energy out, so state 2 and 3 energy in is going to equal to state 9 energy out, so m dot 9 times H9. And here it says the main mass flow rate is 0.05 kilograms per second. I'm going to assume that the main mass flow rate is state 9, but I would ask your professor what the main mass flow rate is supposed to be. So I'm going to put here m dot 9 equals 0.05 kilograms per second. So The only knowns we have are H2, H3, and M.9. Our unknowns right now are M.2, M.3, and H9. And H9 is what we need to find. So we get another thermophysical property value at state 9. So we need to manipulate this equation to find M.2 and M.3. And what we do know is the quality. We do know the quality at state 6, which we found here. And what we do know, so I'm going to write the quality at state 6. This equals M.3 divided by M.6. And this is because quality is a ratio of the vapor mass flow rate over the liquid mass flow rate. So M.3 is all vapor, M.6 is all liquid, which you can see here. State 3, saturated vapor. And state 6, well, we're finding the quality at state 6. So this is our ratio for state 6. Then we know that 1 minus the quality at state 6 equals M.7 divided by M.6. So now, if we were to take this equation that I wrote down, but we divided it all by M.9, so I'm going to take M.9 out, divide that by M.9, divide this by M.9. Now we have ratios of quality. Here's M.2 divided by M.9. Here we have the mass flow rate at state 3 divided by the mass flow rate at state 9. And we know that this value here, so mass flow rate at state 7 divided by the mass flow rate at state 6 is equivalent to the mass flow rate of state 2. I'm sorry. Yes. The mass flow rate of state 2 divided by the mass flow rate at state 9. So this is going to change to 1 minus quality at state 6 and here is just the quality at state 6 that we put here. We'll put X6. And these equations were just to show you how I'm going to get to this energy balance equation, so I can just delete these. We don't even need these. And then as you can see after, we don't even need to know the main mass flow rate, just to find the thermophysical property values. So now we have one equation and our one unknown is H9. So now we can find the rest of our thermophysical property values. We know pressure, and with that first law of thermodynamics, we now know specific entropy at state 9. Paste. 9. Okay, so now we have solved all of our states. Going to calculate solve, and we have no errors. So this is our thermophysical property plot. Again, you can right click this main, you can save, and if you want you can save this as an Excel file if you want to create plots in Excel with this data. Now we can try to make a TS diagram in ease. So we can try to replicate this. So we currently have state 1 going to state 2 to 3. How it's set up now, 3 would go to 4, which would not work out. So 3. Gonna change. How you would probably do this, you would have to rearrange the values. You would have to go here. I'll just show you why this property plot is not going to work out until you change the arrays. So if I go to property plots, real fluids, R134A, I'm making a TS. Just going to get rid of these. Actually, I'll keep my pressure lines in. Our low pressure is 140 or 140. 320 is the medium. High pressure is 800. I hit OK. Now we have a property plot with our constant pressure values. If I were to just put our S and T values down, it's going to be incorrect. Yeah, so if you see here, it's going from 1 to 2, 2 to 3, which is correct. Then it's going to try to go to 3 to 4, and it's just incorrect, but we can adjust this. Just get out of this. So 1, 2, 3. We're going to change state 7 to state 4 for the sake of this property plot. State 7 is now 4 for the TS. And if you were to compute like COP energy values, do not use these new values. This is just for the sake of creating this TS diagram. Okay, so state 7 is now state 4. 1, 2, 3, 4, 5. State 8 is going to be state 5. And now state 7 is state 4. Okay. And now we're going to need a state to connect this line, which is state 8, we're now calling state 5, to state 1, which is the same. The actual state 8, which we're now labeling as state 5, to state 1. So this is going to have to be state 6. So we could do T6 equals T1, S6 equals S1. Okay. Now, I'm going to comment out all these other states just so you can see how when I overlay the TS diagram, I'm creating this one simple cycle kind of. Whoa. Okay. Commenting this out. And these two backslashes are comments, so this means that when I calculate solve the ease code, it's not going to recognize these as functions or values. So we need this, we need this. We don't need the actual state 6 anymore. We're going to comment this out. Actual state 5, we don't need at the moment. State 4, we don't need at the moment. State 3 we're using, state 2 we're using, state 1 we're using. Okay. Now before I hit run solve, I'm just going to check that if I commented these out, it's not going to affect what I did here. It probably will, so that's what I need to check. State 1 was a known, so we're good. State 2 we found state 1, so we're good. Now we need to go to state 3. We're good here. State 7, which is now called state 4. We're good here. State 8 depends on 7. Okay. So if I were to do plots, overlay, I'm going to just overlay it on that incorrect data. So I'll do ST. Going to make this one green so you can see the difference. Oh, this is because I didn't hit calculate solve. So I have a new array table now. Now I'm going to overlay the plot. Right, since we did green last time, I'm going to do this orange. And now you can see the actual states that represent this TS are 1, 2, 3, 7, and 8. So here we have 1, 2, 3, 7, and 8. So now we need to adjust this so that we'll have this upper cycle that connects 9, 4, 5, and 6. So we need to go back here. I'm gonna go state 9. You know what? We will start at state 5 actually. So we're going to start at this state 5. But let's call it of this new thing we're making. We're going to call it state 1. And we're going to create a new array. And I'm just going to denote these new arrays values as up because it's going to be just the upper cycle. So we're calling this P up 1 equals P4, which is going to be that 800 kilopascals. X up of 1 equals 0. Call real thermal props, calling this X up, P up. So now we have state 5. Now we can go to state 6, but we're going to label this state 2. P up 2 equals P2, which has stayed the same throughout this process, so we're leaving that. We have H up 6 equals H up 5, which we found. State 5 is now H up 1. So we see our state 5 is now denoted as 1, so it's H up 1. Find the rest of this. H up. Okay, so now we have 5, 6. We need this 3 because if we just go to 9, it's not going to notice how this is straight and then this is curved. It's a different arrow. So I'll do this right above state 9. I'm going to do connect state 6, which is denoted as 2. Which is going to eventually be denoted as state 4. So this is going to be T up 3 equals T. T up 2 and P up 3 represents actual state 3. And again, remember T up 2, P up 2 equals state 6. So this is just creating a line here. And now we're going to need to create this 3 to 9 line. So we'll go to state 9. State 9 is now going to be called state 4. So we have P up 4 equals P2, which is in this lower cycle, so we're not denoting that as up, it stays the same array. Now we have the quality at state 6, but But state 6 is now denoted as up to, which we found here. Oh, this is a good catch. I forgot to. We need to make this 2. So we have our quality up to is going to be inputted here. So we're going to write X up to. Here is going to be X up to. And our H3, we can still put just a normal quality at H3. Then we have the quality of thermal props, and remember this is P up 4 now. This is H up 4. Now we have our state 9, so we have 5 to 6, 6 to 3, 3 to 9. Now we need 9 to 4. So if we go back up to our state 4, nine is now 4, so we need to call state 4 state 5. So P up 5 equals 800 kilopascals. S up 5 equals S up. State 9 is now S up 4. So this is S up 4. Now we need to change this all. Now we have 5 to 6, 6 to 3, 3 to 9, 9 to 4. Now we just need a line to connect 4 to 5. But here we need an imaginary point, or else 4 to 5 will go like that. So I'm going to do a common here. Connect state 4 to state 5. So we're going to call this imaginary point state 6. So we know pressure is constant, so P up. What would we just do? We'll just do T up of this new state 6 equals the temperature at state 5, which is denoted as T up 1. And we know the quality is a saturated vapor. So we know X up of 6 equals 1. Then to make the TS plot, we need entropy. So we have the T value, we need the entropy value. We have these two properties. We'll go to options, function info. This gives us a whole bunch of information we don't need, so I'm just going to find the specific entropy equation. So here finds entropy. I have temperature and quality, which are known. Paste. Find S up 6. Okay. And now we need to connect this state we just created to state 5, which is denoted as state 1. So I'll put this final upper connection. And now we know the pressure, we know the temperature is the same. Or, sorry, final connection, we just need to make T, so this is going to be state 7, T up 7 equals T up 1. We're making this all equal to the state 5. And then S up 7 equals S. Okay. So now, when I hit calculate, I'll make this bigger. Calculate, solve. 3070, show debug. Okay, so I'm gonna find the error real quick and then we'll get back. Okay, so the error with my code is that I left this as H9 when it's now H up 4. And then I'll check if there's any other errors. So the error came with this mixing chamber energy balance. Because it's H3. And then this is supposed to be multiplied by H2. But, okay, so H2 stays the same, H3 stays the same. So we had two errors. One was I forgot to change the variable that represents state 9 enthalpy, and one was there was no H2 here, which would make this inaccurate. So this will work unless there's another error. Okay, so this was correct. So if I expand this, we can show the array table. And we've separated into different arrays. So now we have T up array and a normal T array. So these normal ones just represent this lower cycle. So we have an array for T's of 1, 2, 3, 4, 5, 6. So now this is 1, 2, 3, 4, 5, and then 6 again. And then now you can see that we have an entropy that corresponds to that. Here we have 1, 2, 3, 4, 5, 6, 7. 7 elements in the T up array, and we're missing one here, so I have to clarify this. We should have 7 in the entropy up array. We go here. Our new states labeled are 1, 2, 3, 4, 5, 6, 7. So now we can make the TS diagram once I find out why S up 3 isn't there. Let me go back to this. 1, 2, 3. So it's in between 6 and 9. And you can see here, I forgot to find the entropy value. Going to copy and paste this. Or you could do options, functions, thermophysical properties. We need an entropy in the up array at state 3. Now, when I hit calculate solve, let's see, oh, okay. Here I accidentally have quality, but here my known values are P and T. So we have pressure, temperature. Okay, let me see if that produces an error. Let's connect state 6 to state 9. Okay, so we're going to use quality because, oh yes, because this is just basic thermodynamics. This is their constant pressure line. So here we specify temperature and pressure, but when working fluid's changing from saturated liquid to sat vapor, it can't tell what the quality is based on these values, and it can't tell the entropy. Like it could be, the entropy could be any range of these values within this. So we need to denote that there's a quality of 1 because it's sat vapor. So I'm going to do x up 3, x up 2, and change this back to quality. So there's no errors, but it's just not. There we go. Here we can see that it's all fixed. And now our missing entropy at state 3 is found. So I can go plots, overlay plot. I'll do this one in a different color. I'll just do, I believe this is black. So our x-axis is going to be S up. Our y-axis we're going to label T up. We're going to put OK. And you can see how it came up. So now we have the complete chart. And just to clean this, I'm going to delete this and create a new property plot. R134A, real fluid, TS. We have our minimum, we need our minimum maximum pressures. 140, 320, 800. Okay. See, these were the lines created. Now we're going to overlay the plot. First, we will do, and we'll remember to keep this consistent, so we have orange here. With these arrows, we'll hit OK. Missing data in row 7. Row 7. 1, 2, 3, 4, 5, 6. That should not matter, so we'll see what happens. Okay, so I don't know what that error is because it looks fine. Then we're going to overlay onto the same plot again. We're going to make it the same colors. Oh shoot. Can't see with my night mode what color it was. Hopefully it's this color. Now we're going to do the S up and the T up. Ah, I choose the wrong color. But this should be correct. I must have made a small error, but we can zoom in and look. It's pretty close. If I look back here, the worksheet, we have I think this is actually how it's supposed to look. We just forgot to add a connection here. So 1, 2, 3, 4. So we had a small error in this connection, but it's kind of close. And then we can zoom in more on our error. So we can see it goes there. It's just that I believe this value. Well, we forgot to have a connection, so we forgot to add this connection point. Instead of this line going straight across, it would go down here and then here. But if we were to assume I didn't make that error, we would right click this, we'd do save. You could open up a Word document and insert this TS diagram. And you can do the same thing for a pH diagram. There. So, had a small error there, but it would be correct if I would have just made an extra node or element in the array to connect these two lines together.